Yes, thank you, Jiwang. I appreciate the introduction and the invitation. It's nice to be with you all. So this is joint work with my recently graduated PhD student, Nikos Kargas, who joined Amazon Research in Cambridge, UK, about a month ago. And the problem I will be talking about is what is known broadly in computer science as the supervised learning problem. And the basic problem is like this. You have a certain function or system, you may want to call it, that takes input vectors and outputs scalar or vector outputs, and you observe input-output pairs, and you are trying to figure out what the system is. This is what is being done in numerous machine learning tasks, classification of binary or categorical variables, regression, but also in imaging tasks, for example, in MRI reconstruction, where actually the inputs and the outputs might be complex valued. So you see a collection of input-output pairs, and you're trying to figure out what this operator is, right? And as I said, there are applications where this is a categorical variable, the output is a categorical variable, or it may be a real or complex variable. In particular, in imaging applications in electrical engineering, it is a complex variable. And what is the most popular, most successful, I would say, method nowadays to treat problems of this kind? As you all know, it is neural networks, and deep neural networks in particular, which work remarkably well in certain situations, but for the most part, we don't understand why. Choosing the right architecture to make them work is more of an art. And even when they work well in mimicking the input-output relationship of the system you have, they're hard to interpret, right? Another thing that I would like to add is that being trained in many years ago as a disciplined engineer, I would say that the success of these structures has been sort of against all odds and principles, and we'd like to understand why. Because being an engineer, you cannot ignore the fact that these are working so well in so many applications, right? So, what is this talk about? This talk is not about neural networks. It is about the supervised learning problem. But I will try to give a very simple but principled alternative. And it is based on tensor decomposition and tensor principal components. This is an area that I've been working in for over 25 years. I started working on tensor decomposition, low-rank tensor decomposition, back in '95, I believe. Initially, mostly worrying about uniqueness and applications in communications. And more recently, I've been working more on modeling aspects. And so what are the advantages of this approach? First of all, as you will see, it is, in quotes, universal. So it can model or approximate any reasonable operator, let's say. It is intuitive. It is interpretable, at least if you understand tensor decomposition, and it is backed by some theory. There's a lot more to do, of course. And it has certain advantages that you cannot find in neural networks. For example, it naturally works with incomplete input data, which is very important in practice. And what I mean by incomplete input data is during training as well as during testing, right? The actual use of these approximations. One or more of these inputs, hope you can see my pointer, excuse me. One or more of these inputs, let's say X2L here, is missing, right? Maybe 90% of your input variables are missing, and you still wish to train from them, right? You don't have access to those variables. You still wish to train from incomplete input-output pairs or regress or predict from incomplete input-output pairs. That's an important problem in practice. Okay, the applications of this abound. You can find, of course, applications in machine learning, but also in dynamical system identification and control. So basically, this is the system identification problem, the nonlinear system identification problem. but also in wireless communications and other domains. So many applications. Now, if you are trained in system identification, then, you know, if the operator F is linear, you know everything about this problem, right? If it is nonlinear and it is not structured nonlinearity, we know very little about this problem, right? And one wonders about conditions for uniqueness of your estimate, performance, complexity, both computational complexity and sample complexity and other things, right? So there are a lot of questions. I will show you applications because being an engineer, I'm not satisfied just proposing a method. I want to see it work in practice, work with real data, and I will show you examples of how this thing works with real data. Some of the examples are about course grade prediction, trying to predict a student's course grade given historical grades from that student and other students. I had an NSF project on this topic several years ago. It is scary that you can predict well, being an academician, being a teacher, right? But there are other applications like in drug response prediction, how well a given patient with a given, you know, given genetic information, given, you know, other health indicators will respond to a particular drug. Text classification, music classification, in wireless communications, which is one of the areas I'm working on, channel estimation, channel prediction, which are very important in 5G and beyond 5G. All these can be viewed as applications of the framework. All right, so what is nice about what I'm going to be talking about, it's a very simple model. It's a very simple approach. It is based on low-rank tensor decomposition. It can model highly nonlinear operators, and it can offer identification guarantees under certain conditions. And I won't go for this audience over the canonical polyadic decomposition and tensor decomposition, because I assume that everybody here knows about this. But a key property that we will be using is that low-rank tensor decomposition under certain conditions is unique. And in fact, even low-rank tensor completion under certain conditions is unique. So we will be using those properties to claim that under certain conditions, we can indeed identify the function, the unknown function F. Okay, and I'll be using the O dot notation here for the Khatri-Rao product, and this circle notation here for the outer product. Okay, that's more or less what you need to know. So let us talk about modeling of nonlinear operators or nonlinear functions. So as you are all well aware of, any linear function of a certain vector x can be represented as an inner product, right, of a vector of weights and that vector x. If you have multiple linear functions, it's a matrix times a vector x. Any quadratic function can be represented as a quadratic form where W is a matrix of coefficients, right? And therefore, I can model any quadratic operator as x transpose Wx for a suitable choice of W. And if I want to include lower order terms, linear terms, I simply stick a unit at the end of the vector x, and then I produce all linear things as well. And if I want to produce polynomials of order 3, right, I stick a unit at the end of every vector x, and I can think of polynomials of order 3, right, as basically a tensor of coefficients, right, which you hit from the left, top, and right with vector x, right? So this has been used to model polynomials of a certain degree. It has been used to model recommender systems by Rendel 11 years ago. And the key problem, of course, is that when the degree of the polynomial grows, you have a higher order tensor, and the number of coefficients blows up exponentially. So you got to do something about it. And what Rendel and others suggested was to assume that the coefficient tensor is low rank, and that controls the complexity of the model and allows you to generalize, right? However, this approach has drawbacks. You assume knowledge of the degree of this function f, that can be restrictive. You cannot go to very high degrees because the number of parameters grows with D. If you want to have very high degree polynomials, you still need a very large number of parameters. So all of these are restrictions of this approach. So our basic idea, what started our work here maybe 2.5 years ago, was a very simple observation, right? The observation is every time I give you an input-output pair, so I tell you that f of x1, 1, x2, 1, x3, 1, so I give you that one example of input, that's a superscript, right? F at that input is equal to y1, then what I do is I give you an element of a three-way tensor. So if you collect all the input-output pairs that you have, what you have is elements of this tensor, right? And if you wish to know what this function f is, what you are really asking is, how can I predict the elements of that tensor that I haven't seen, right? Which are the majority, of course, right? So the question is, I give you input-output pairs, I give you samples of elements of a tensor, figure out the rest of the elements, right? So essentially, one can view this input-output nonlinear system identification as a tensor completion problem. And if the inputs are not 3, but 3,000, who cares? The math is the same, the methods are the same, right? Computationally, we need to be able to do something to scale up to this kind of 1,000 ways, right? Tensors, but in principle, this is something we can do, right? So this was the beginning behind our work in this area. And it's not as simple as that, but this is in a nutshell the basic idea. So if you have inputs that are categorical, right, finite alphabet, so each one of them assumes a finite number of values, right, then you can think that nonlinear system identification is tensor completion, right? So what are the advantages of this? First of all, you can model any nonlinearity, even of infinite order, if you allow high enough rank. Even with rank 2, 3, 4, you can model very highly nonlinear discontinuous, completely discontinuous operators, which you cannot do using polynomials, right? You can claim provably correct system identification from limited samples, right, under existing low-rank tensor completion results, right? And, you know, being an engineer, I know that no tensor in real life is low-rank, but just like taking your picture, taking a singular value decomposition and keeping the 10 principal components, throwing away the rest, reconstructing your picture, I can still recognize you, right? The same thing happens with these Fs, right? With these systems that I'm trying to identify. So I can still approximate, right? And I can identify essentially the principal components. Now, I claim that I can model highly nonlinear. How highly nonlinear? Let me give you a few examples. If the function that you are trying to model is separable, right, then in fact, the tensor that you are trying to model is rank 1, which is very simple, right? NP-hard in theory, but in practice, you can approximate it very well, right? And you can learn it very fast. If you have a sum of separable functions, right, n is the number of variables that you have, then the maximal rank of this is, of course, n. So it's, again, very low rank. If you have a sum of pairwise nonlinearities, right, so the total nonlinear function is a sum of pairwise nonlinearities, or other low-order cliques, if you want to think of it this way, then the maximal rank is, again, in squared over 2, which is much, 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 much less than the maximal possible rank. And you can generalize this. I'm not going to go into this, but at least you get an idea that you can indeed model highly nonlinear functions with low rank. So what is the problem formulation? It is quite simple. In the simplest case, the problem formulation, you do a least squares formulation, right? So least square system identification. You are trying to find a low rank CPD model, right, which approximately reproduces the samples of the tensor that you observed. You may want, so you do this constraint down here. So the X here is a low rank model, right? And again, this O dot is a categorical product. And you also include a rank regularization term. We found that this helps out in applications. If you have data sets that are, variables that are ordinal, right? Then you can also incorporate smoothness constraints as regularizers. I'm not going to spend too much time on this. But again, if you have ordinal variables, this works well in practice. So I'm not going to tell you details about identifiability of tensor completion, but there are two types of results, probabilistic and deterministic results. If you can sample the input systematically, the input sample systematically, then you can have much better results than random sampling. I have some references here at the end of the talk.
Nikos, sorry, GM has a question. He asked, what is the circled star notation?
The circ notation is outer product. The O dot in LaTeX is Katri-Rao product.
Okay.
Thank you. So if you can systematically sample input-output pairs, you can have much better identifiability results, and you can take a look at those references. Right. Because of the time limitation, I will skip the details here. But there are results that we can use, and these are not new results for our work. The algorithm, we have two types of algorithms. Both of them exploit sparsity. One is based on alternating optimization. For large-scale problems, that doesn't work as well. So if you have a few thousand variables, you need to do something else. And we have follow-up work for this. But basically, for large-scale problems, we use stochastic gradient or block stochastic gradient descent. Something I alluded to earlier, what happens if we have missing elements in the training data and or the testing data? What we do is we combine two pieces of our work. So it turns out that you can naturally and easily marginalize the missing variables using a coarse estimate of the joint PMF, of the joint probability mass function of the inputs. And again, you can take a look when you get a chance. I'm not going to spend time here now because it will take a while to explain the notation. But you can actually train and test with missing data, which is a big advantage. You can find the details in this paper in AAAI 2020. You can also do multiple outputs, not a single output, by simply augmenting the CPD decomposition that you're using with another mode, right? Which is represented here by the loading factor or matrix factor V, which actually takes the latent variables and outputs multiple outputs. And this is basically comes almost at no cost in terms of algorithm or complexity. So you can actually do multi-output regression naturally using the same model. Let me show you some experiments with real data. I will first show regression tasks using UC Irvine datasets and a grade prediction task. The way we do this is we split the available data into 80% training and 20% testing, and we use 5-fold cross-validation for parameter selection. We only have very few parameters. The key parameter is the rank of the tensor and the lambda regularization parameter, the rank or smoothness regularization parameter. So very few parameters. And we pick them automatically through cross-validation, right, over the training set. So here are several data sets from the UCI repository and several other data sets from the computer science department at the University of Minnesota, where I used to work 4 years ago, trying to do grade prediction. And so you will see that the number of variables is relatively small here, 19. We have now gone to thousands using slightly different techniques. And these are the number, M is the number of training samples. So these are difficult data sets, right? The number of training samples is not great. All right. And what we're comparing to here is for various data sets. So we are reporting root mean squared error and standard deviation of root mean squared error for the various data sets, the rows of this table. And we're comparing with ridge regression, support vector regression using radial basis functions and polynomials, decision trees, a decision tree algorithm, and a multi-layer perceptron, which is a neural network optimized with respect to the number of layers. And what you will see is that our approach, which is very simple, principle-based, using tensor modeling, actually gets the best or very close to the best results in all cases, outperforming all algorithms here, which are actually designed for this task, right? So support vector regression is a specialized regression algorithm, right? Ours is not a prediction algorithm, right? It's not a regression algorithm. It's a modeling, right? A tensor modeling algorithm, which can be used to predict. So you see much better in some cases. For example, if you look at this, what is this? Parkinson's datasets 1 and 2, right? We get an RMSE of 133 versus 240 for the best other method and 360 for a neural network. So that's significant. Let me skip this because it's grade prediction. That's another interesting problem. It's tougher than other prediction problems, but still you can do actually very well. Again, you will see that here we compared with biased matrix factorization, which is the state-of-the-art sort of recommender system approach, and with a raw GPA estimate, predicting a student's grade as the student's GPA up to that point. And you will see that we're doing, again, better than the state-of-the-art in most cases, or close to it. All right, so I want to spare my last 5 minutes or 6 minutes to talk about the continuous case, which is more interesting perhaps. So, so what happens when the inputs are continuous, right? So then the function is not naturally a tensor. One way to address this is to discretize, to quantize, of course. The question is how much should you quantize, because there are interesting trade-offs between resolution and generalization and complexity. So we want to have an alternative approach. So what would be an alternative approach? And since I'm a signal processing guy, the first thing that came to mind was the following. Let us assume that we have a function.
So Nikos, you have 5 minutes.
Thank you. I will go quickly. So if you have a function that is compactly supported on an interval, let's say 0, 1, we can always scale the support to 0, 1. Then we can represent that function using a Fourier series, right? And we can do even periodic extension, for example, and use a Fourier series. Now, we can do this, and the reason of doing this, of compressing the support to 0, 1 and using Fourier series, is because we basically put the problem back into a countable coefficient estimation form, right? So I went now from an uncountable to a countable problem. And of course, the next thing is that I will assume that this function f is sufficiently differentiable, and I will truncate. And the same thing can happen. I can truncate the Fourier series representation, right? The same thing can happen in the multivariate case. Everything follows, right? And we can have an approximation, of course. It's not going to be exact, but we can have an approximation, right? Which is now going to be a tensor, because I have a tensor of Fourier series coefficients. The number of ways of this tensor is as many as the number of variables in the input, right? The size of its mode of the tensor, right, corresponds to the number of Fourier series coefficients that are important for representing my function. It is interesting to note that if I give you, samples, random samples of the input, then you can very naturally estimate this using a sample average. So computationally, that's nice, right? So now we have managed, by using a Fourier series, right, and truncating the Fourier series, we have managed to go back to a finite order tensor problem. But the challenge is that the number of Fourier coefficients grows exponentially. So we will play again the same trick. We will assume a low rank parametrization of the Fourier series tensor. So we introduce a parametrization, a low rank parametrization of that, and we learn the parametrization. So we learn directly in the Fourier series domain. Okay, and I'm not gonna show you examples. Actually, the low rank parametrization helps reduce the variance as well, right? As you might expect. We have two algorithms to learn this model. One is direct, the other one is indirect, without ever actually computing the Fourier series tensor. And I'll skip the details. You can look it up in the papers. How well does this work? Well, I'll give you two examples. One in which the true function is a neural network, and when the true function is low rank. When the true function is low rank, what you see here on the top left figure is that, of course, our approach outperforms any other approach, including neural networks. When the true function is a neural network, right, our approach actually gets close to the estimation results that you get with the correct neural network architecture, which is here the ReLU neural network. And it's actually better than using the same neural network architecture with a different nonlinearity. So this tells you that this tensor modeling, right, in the Fourier series domain actually can discover the neural network architecture, at least in simple examples, right? Okay, and real results with real data sets. I'm showing here again various University of California, Irvine data sets, real data sets. And what I'm showing is mean squared error performance of our method versus various other methods, including neural networks. And if you look at the bold face, these are the winning results. You will see that the method works very well. So our method is on the right, CSID and FSA. The latest method is all the way to the right, the Fourier series approximation, hidden tensor factorization. So in many cases, for example, let's take this EE1 data set. The best neural network gives you mean squared error of 0.31. Decision tree is 0.30, right? Our previous discretized approach, 0.18, our latest Fourier series approach, multivariate Fourier series, 0.16. So these are significant. That's 50% reduction relative to the neural network. Okay, so take home points, and I'm going to be right on time. The key message here is that nonlinear system identification or nonlinear function learning from input-output samples is tensor completion. You can view it as a tensor completion problem, right? The benefit of doing that is that you have probably correct system identification under low rank conditions. And whenever we have new results in the area of tensor completion, we can apply them to this problem as well. I have argued that low rank models can actually model highly nonlinear functions and real world functions, because success with a real world data set says that, yes, real world functions are approximately low rank. And even if they are not low rank, right, they're approximately low rank, and we identify principal components, right? And with this, I will stop, and I'll be happy to answer any questions that you may have.